So, good morning, everyone. So, we are now continuing from the place we had left in the last class in the matter of the plastic analysis. So, last class we had seen the assumptions in our analysis. So, essentially, we have idealized stress strain diagrams. We assume that both in compression and tension, the stress strain diagram, Young's modulus, and the ultimate strength, they are all same. And we are also considering basically pure elastoplastic model, and there is no strain hardening. Now let us understand how does failure happen by plastic mode. Plastic. So we have here a beam, and this beam is under arbitrary loading, and deliberately we have chosen a section which is monosymmetric. So you hope are able to see this section, and this is monosymmetric, so it's symmetric about the y-axis but it's not symmetric about the x-axis. So what do you think the neutral axis would be? It will be towards the downside or towards the upside given the shape of the section. So you can give your response. So neutral axis would be towards the downside because downside has greater area, so it is towards the downside. So if we plot the distribution of stress along the depth of the section, it will be something like this. So what do you observe? Neutral axis is towards the downside because we have greater area over there, and because of this fact the top compression stresses, they are higher than the bottommost tensile stress. So that means the limit will be reached first in the compression phase, that is the top phase. And in other words, we can say that the Z of the compression side is lower than Z of the tension side. And what is Z? Basically Z is nothing but it's equal to the moment of inertia divided by the distance of the extreme fiber from the neutral axis. So that is here YC. So this is ZC, and YC is basically this distance. Alright, so that is the section modulus. So it will have different section modulus with respect to compression and tension. So the section modulus of the compression side is lower than that of the tension side. Okay, let's go further. So we assume that plane sections, they remain plane, and further let's increase the loads gradually. So all the loads, if this UDL, we are increasing it by a certain factor gradually, and by the same factor we are increasing the point loads also. So all the loads, they are just increasing by the same multiplication factor gradually. And what will happen is that the section, its state is being represented here. So what we are doing is that the curve on the top is representing the tension side, the bottom phase, and the curve on the bottom, it's giving us the top or the compression phase. So this is maybe you have to be familiarized that since we show tension as positive, so tension which is happening at the bottom phase is appearing here at the top. And what are these points 1, 2, 3? These are the states. So when we are loading, so before loading we were at 0 state, no stress anywhere, and then when we have started loading, we have increased the load such that we are at point number 1. So point number 1, in the top and bottom they have different stresses, so naturally compression side stress will be higher. So we can see here also that the stress on the compression side, that is top, is larger than that on the tension side. But the thing is that the behavior is still elastic. Both tension and compression zones, they are in the elastic limit because we have not reached the yield point. Okay, so here we have again drawn the stress diagram. So this is the compression side, this is less than the yield stress, and this is the tension side, this is also less than the yield stress, but the compression stress is greater than that of the tensile stress. Like the way it is shown at the top, we have the compression stress is higher than the tensile stress. So this is our cross section. And now how do we determine the neutral axis? How do we define neutral axis? So neutral axis is basically that line on one side of which we have tension, other side of which we have compression, such that the tensile and the compressive forces, they are equal to one another. So that's how we define the neutral axis. So that is, there is no net axial force in this section. So how do we do this? So we set up the integration over the area. So here the width of the section is variable. So this is the stress, and we are, let's say, treating the tensile stress as positive and compressive stress as negative. Alright. So any doubt till now? I am now going to change my slide. So we do this integration. Now the stress is given by using the Euler Bernoulli's beam equation. So we have the elastic neutral axis, and we yet do not know what is the distance of the neutral axis from the bottommost. So bottommost we have taken as the origin of the y-axis, and now, so what the stress will be governed by this term y star, that is the distance of the particular section from the neutral axis. So that's what we have done here. So y star is y minus ye, and we substitute it into the integration. This integration, this defines that there is no net axial force, and when we substitute and we solve it, and we can take out something common. So because m and I, they are constants, they can be taken out, and similarly ye can be taken out. So this gives us the value of the neutral axis. So this is how we determine the neutral axis. So what we have to do is, we have to choose an origin and take moment of the area about that, and from the first moment of the area, once we divide it by the total area, we get the neutral axis position. So this happens in the case of the elastic sections. Now we increase the load such that we are able to reach point number 2. So what is point number 2? So point number 2 is here, that point number 2 is at the top and bottom. I am drawing the locations. So point number 2 is, in the case of the top, it's just located at the boundary, that is, it's the yield point. So when we are increasing the stresses, so at the top we'll encounter the yield point, and that's here, and at the bottom we will still not have reached the yield point. And the reason is that the section is such that it's on the higher area on the downside, so that the neutral axis is a little bit downwards, it's not at the middle. So now what happens at this particular point, when we draw the stress diagram across the section, it's like this. We are drawing the strain diagram and the stress diagram both. So what we find is that at the compression phase, that is top, we have reached the yield strain, and the corresponding yield stress has reached. So basically the section is still at the limit of the elastic zone. So at the bottom we still have some scope of further increasing the stress till it reaches the yield point, but at the top, that is compression, it has reached the exact yield point. So if we increase the load further, then the top portion will definitely go in the plastic zone. Alright. So we have reached yield condition at one point. And now what is this angle equal to? If we try to measure this angle either in the strain diagram or in the stress diagram, what this angle tells us in general? This angle tells us about the curvature of the section. So tangent of this angle is equal to basically the curvature, and because the curvature itself is very small, so this can be approximated tan phi can be approximated as tan theta itself. So basically this gives us a measure of the curvature of the section. And what is curvature? Curvature is basically the inverse of the radius of curvature during the bending of the section. So this is the curvature. So here we are just considering the positive quantities, but if we use the strict sign convention that will show all tensile stresses and tensile strains as positive and all the compressive stresses and compressive strains as negative, then we'll get something like this using the sign convention. So if we use sign convention, because we are showing the top strains which are compression as negative, so we'll use here minus sign. And D is the overall depth of the section. Alright, so I hope the slides are changing correctly and you are not encountering any problem. So what happens is that if the curvature comes out to be positive, that means that the surface is undergoing deformation such that concave surface is towards the upside, just like in the case of the sagging conditions, and in the case of hogging conditions we'll get negative curvature. So we can derive this also. So all you have to do is that let's say we have the beam and the beam undergoes deformation and the neutral axis is shown here, and neutral axis it may be monosymmetric section or it can be bisymmetric section. YT and YB are the distances of the extreme fiber from the neutral axis, the top and the bottom. And what we do, we take a small element of this arc, and this is very small. Let's say this angle is small angle theta. Then the original length was r theta, undeformed length, and at the top fiber this would have been reduced because it will undergo compression, and at the bottom it will increase. Then we can get the strain at the top and strain at the bottom just by using the fundamental definition of the strain, that is the change in length with respect to the original length. And then from these we have this expression, we have the strain and we have the radius also. What is radius? Radius is basically, this is the radius of curvature r, and inverse of this is basically the curvature. So then with this you can very easily derive our required relation, that is the curvature is equal to the sum of the top and bottom strains, their positive values, and divided by the depth of the section. So what we find is that we have reached here the yield moment, and where the yield stress has come at the topmost fiber. Bottom we still have stress less than the yield stress. So here we can find out the exact value of the yield moment. So all we have to do is that, because top is governing, so what we have used is that we substitute here the value of the y compression, and at the top we have the stress equal to sigma y, so we get here the yield moment. So this is the yield moment of the section, and it is governed by the compression side here. So what is Z? Z can be with respect to tension, Z can be with respect to compression, but as a general rule Z will be dictated by the lower of the two values. So this is called as the elastic section modulus, and we define it like this, that it's equal to the I divided by the greater of the two distances of the extreme fiber, either the top or the bottom, with respect to the neutral axis. So this neutral axis is the elastic neutral axis, that's why we are using ENA. NA stands for neutral axis, E stands for elastic. Okay, so basically we have to use the larger of the two fiber distances, that will define the neutral axis depth suitable for the section modulus. Now let's go to point number 3, and point number 3 is such that the tension side and compression side both are now yielding. So now what happens on the compression side? Compression side, we had already reached the yield point. So the compression side has moved a little bit further. And the tension side, we have reached point number 3 such that it's just the yield point. But the section has not yet ruptured. Why it has not ruptured? Because we assume that the metal is highly ductile. It can still carry further loads. So now if we see here that earlier in the top we had reached the yield point and not at the bottom, but now bottom is also in the same category. And what we find that the strain at the top, it has shooted beyond the yield strain, and at the bottom we have just reached the yield strain. So if we now draw the stress diagram will be something like this, because now we are exceeding the yield strain at top. So stress cannot exceed beyond this point, so it will not go linear like this, but it will just truncate here. So this part will not be there. All right. So here we have reached the yield stress now. So at the bottom we have definitely yield stress, but at the top we have a particular height of the section starting from the top where there is no further increase in the stress. So basically in this zone, this shaded zone is the zone where we have full plastic region. So this zone depth X is having full plastic zone. So this is now no longer the elastic neutral axis, and it's also not the fully plastic neutral axis, it's something in between. Alright, so now the stress is no longer proportional to Y. So now we stress the beam further, we increase the load such that we are now going to point number 4. So what is point number 4? Point number 4 means that both on the tension and the compression side we have exceeded the elastic limit. Okay, so we are now both the top and bottom, we are beyond the yield point. And of course now if we see the tension side as compared to the compression side has drifted further away from the yield point as compared to the tension side, because of the nature of the section, that the structure, the beam section is such that it has more area towards the bottom. So now the strain diagram and the stress diagram will be like this. So what we observe is that there is a plastic region both on the top and the bottom. So beyond a certain distance we have fully plastic region, that is both the compression side and the tension side we have plastic zone. But then in the middle, this distance which we call DC, or the elastic core, we have elastic region. So this is called as elastic core. So we have a combination of the elastic and the plastic regions. So the elastic core, its dimension, its depth is DC. So this provides basically a measure of the curvature. So curvature, basically we can, earlier we were getting like this, but now this region we have the, we can use this to define our new curvature. And this stress and this strain we know, so the strain at the top is epsilon y on both the tension and the compression extremes of this elastic core. So we divide it by the depth of the core, so that gives us a measure of the curvature. If we increase the loads further, what will happen? The plastic regions will increase further and the curvature will keep on increasing further and further. Now what will happen? The limiting situation, that the top plastic region and the bottom plastic region, they just meet each other. So in that particular circumstance we are going to point number 5. So point number 5 is illustrated here. So we have this kind of situation that the entire compression and the entire tension zone, they have the extreme value of the stress, that is the yield stress. And now this particular situation, the neutral axis is the actual plastic neutral axis. So how do we define this? We again have to define by the equality of the compression and the tension forces. Now note that in this particular case, what will be curvature? Curvature will be infinite. But we assume that the section, it has still the capability to resist any kind of rupture. So the plastic moment capacity is there, and the conditions are such that the section can develop it. It does not fail prematurely by some other reason like buckling or by rupture of the material itself. So we assume that the material itself is very ductile. So this is the plastic neutral axis, and now we try to derive the equation for the expression for the plastic neutral axis. So basically, once we equate for this particular condition where curvature is infinity, once we equate compression and the tension, so what we get is that the plastic neutral axis is defined by the equality that the two areas, they are equal. And this is from common sense also we can say that because the yield stress is same in compression and tension, so the two areas have to be equal. So this is different from the elastic neutral axis. So elastic neutral axis, we were using the first moment of the areas to get the location of the neutral axis, but here the neutral axis location is defined by the fact that the two areas, the compression and the tension areas, they are equal. Okay, so basically plastic neutral axis, it divides the section into two equal areas. So if for example we have a bisymmetric section like I section, which is a doubly symmetric section, then elastic and the plastic neutral axis, they will be just the axis of symmetry. But if it's a monosymmetric section like this one, then which is symmetric about y-axis only, then the elastic and the plastic neutral axis will not coincide. Okay, so basically now we have here, let's say the CGs of the two areas, A1 and A2 are the two areas, one in compression, one in tension, both equal, and their respective CGs are also shown, Y1 and Y2. Now we derive an expression for the plastic moment. So what is the plastic moment? Plastic moment is basically we have one side we have compression and the other side we have tension. So their values multiplied by the lever arm will give us the value of the plastic moment. So this is what is the plastic moment. Sigma 1 multiplied by area 1 is the compression force, sigma y into area 2 is the tensile force, and we are multiplying by their respective neutral axis depths, and then we get this expression. So this is the expression for the plastic moment. Now if we compare with the expression for the elastic moment, this term is something like equivalent to the Z. So this is called as the plastic section modulus. We define our plastic moment as sigma y multiplied by the plastic section modulus, and this plastic section modulus is given by this expression. It's equal to the half of the total area of the section multiplied by the lever arm of the two forces, or it's basically the shortest distance between the centroids of the compression and the tension forces. And then we define shape factor. Shape factor is equal to the ratio of plastic moment to the yield moment, or the ratio of the section modulus for the plastic and the elastic case. So that is equal to the shape factor F. Okay, so we just stop here. So if you have any doubt or anything, you can just raise your hand on what we have covered. So if no doubt, then I think we just go to the attendance. So Ankish Chaudhary, are you there?
Yes,
Okay. Asif Ali Khan, are you there?
present, sir.
Okay. And then we have Deepak Berwa has left. Dharam Singh,
Present, sir.
Parmar Hardik, he has left. Kritika Leela, she has also left. Manish Gopal.
Present, sir.
Manish Kumar Meena.
Yes, sir.
Okay, present. Mayank.
Done, sir.
Namrata.
Present, sir.
Okay. Rahul Dabar.
Present, sir.
Sahil Garg.
Present, sir.
Varun Kumar.
Present, sir.
Amrendra Kumar Jha.
Present, sir.
Suresh Singh Mehra. Major Suresh Singh Mehra.
Present, sir.
Pawan Kumar.
Present, sir.
Alina.
Present, sir.
Shubhra Jyoti Jaina.
Yes, sir.
Nikhil Kullar. I think he has left. And Karan Faiz.
Yes, sir.
Okay, fine. Were you able to hear me properly? If you were able to hear me properly, then raise your hand. Very good. And now you can just lower your hands. I'm asking next question. Was there any interruption with regard to my voice in between? If there was any interruption you encountered, just raise your hand. So that means there was no interruption. Now next question. Was there any interruption regarding the slide progression? Did you encounter anything like my slide is freezing? If you encounter this kind of situation, just raise your hand, else you keep your hand lower. That means there was no problem. Now my third question is that you have seen both the ways of teaching. In fact, you have seen 3 different ways of teaching. First way is that I pre-record a PPT and upload it. You watch it during the designated time and then we have the question answer session. This is one way. Second way is that I record my presentation using the document camera, for example the case of the flexibility approach, and I upload it. You watch it and then you come for question answer. That is method 2. So we have method number 1, method number 2, both are pre-recorded, but in method number 1 we are using PPT, method number 2 we are using document camera. Now the method number 3 is this live, which we have today experimented and we had experimented in the last class also. So if you believe, if you based on this experience, if you think that you are more comfortable with pre-recorded way, the way we were doing before as compared to the live, then you raise your hand, else you keep it down. Okay, so majority has viewed that pre-recorded thing was better than the live session. Okay. Now let me ask you some question regarding the last class. You can lower your hand. Last class we had the live session. Was the interruption major during the live class? If it was really major interruption, then you raise your hand. Yes. So last class there was a major interruption, it seems. So my next question is that in the pre-recorded, which you find better? I do it with hands and use document camera, or I use pre-recorded presentation. So if you believe option number 1 is pre-recorded presentation, option number 2 is pre-recorded hand camera thing. So if you are going with, if you support option number 1, that is pre-recorded PPT, over option number 2, that is pre-recorded hand camera based teaching, then you raise your hand. So understand my question. If you believe that pre-recorded PPT is better than pre-recorded document camera based recording, then you raise your hand. Else you keep it down. Let me interchange the question. If you think that pre-recorded document camera based teaching is better than the pre-recorded PPT, then you raise hand. Okay, so you believe that pre-recorded document camera thing is better than the pre-recorded PPT. Okay, fine. So thank you for your valuable feedback. And now on the teaching method, you can, if you have any comments, any suggestions, because you are the users, and your suggestions we will implement, and these will also be benchmarked. So if you want to say something, raise your hand and I'll give you the opportunity to speak frankly. So fine. So now if you have any question related to what we have covered today, then you raise your hand. Plastic analysis, deliberately I have kept the coverage less because so that we can have more discussion, and the other reason is that in the online teaching the attention span is less. We cannot go on for hours and hours, so we must give break and interact freely, because already you are overloaded with online content. So have any question regarding the plastic analysis, just raise your hand. But today we did not have any interruption thanks to the networking. So you have any doubt, anything, just raise your hand regarding the plastic analysis.